everyone. In this video, we're going to talk about even and odd functions. Okay, so we're just going to start with the definition for even and odd functions. So let's say that f is a function. F is even if f of negative x is equal to f of x for all x in the domain of f. So what that means is if we replace x with negative x in the equation and we simplify, it would simplify back to what we started with. It would simplify back to the original function. And a function is an odd function if we replace x with negative x. So if f of negative x equals negative f of x for all x in the domain of the function. So that is saying if we're given an equation and we replace x with negative x and we simplify, we're going to end up with the opposite of the original function. Okay, so the signs of each term will change. Okay, so what does this mean graphically? If a function is even, that means that its graph is symmetric with respect to the y-axis. Okay? If a function is even, its graph is symmetric with respect to the y-axis. So that means if we were to flip the graph over the y-axis, it would land on itself. Okay? You would get the same graph, basically. If we flip the graph horizontally, it's going to look the same. And let me just explain, too, what's going to happen with your ordered pairs. Let's just say that the ordered pair of this point was, I'm just going to call it 3, 4. The coordinate of this point would be -3, 4. So notice that your x-coordinate is opposite. Okay, so if you're ever looking at a table of values and you're comparing two functions, if all the x-coordinates are opposite but the y-coordinates are the same, then you know it's an even function. Okay? All right, when a function is an odd function, then its graph is symmetric with respect to the origin. So that means if we rotate the graph 180 degrees around the origin, we will get the same graph. Let's look at some ordered pairs. Let's just say that the ordered pair for this point was, I don't know, to me that one's looking more like maybe 4, 3. That means the coordinates of this point would be -4, -3. So notice this time your x-coordinate and your y-coordinate are opposite. Okay. All right. Let me show you some more graphs so that you'll hopefully understand this. So these are all examples of even functions. And I just want to show you that all of these graphs are symmetric with respect to the y-axis. Because if we flip the graph horizontally or over the y-axis, it will look the same. Let me flip this graph horizontally or over the y-axis. Again, it still looks the same. And then the same thing would happen with q of x. If I flip the graph horizontally, it still looks the same. Okay, so these are all graphs of even functions. Okay. Let's look at some equations. All right, so given an equation, how do we determine if the function is even? So it's all about replacing x with negative x. Okay, so if we find f of negative x and we simplify, if we end up with the same equation that we started with, then we know it's an even function. Let me show you how it works. All right, our first example, f of x equals 2 times the absolute value of 3x plus x squared. So I'm going to replace x with negative x. And then I'm just going to simplify. Okay, I'm going to start in the absolute value. 3 times negative x is negative 3x. If I have negative x squared, that would actually equal positive x squared. All right, and you guys, absolute value, remember, is always positive. So notice when we simplify, we get back to the original equation. So therefore, this is an even function. All right, next example, g of x is equal to 2x to the 4th plus x squared. Again, we're going to start by replacing x with negative x. And simplify. So remember, if you have a negative base and you raise it to an even power, you're going to end up with a positive value. So this is just going to simplify back to 2x to the 4th plus x squared. We got back to the original, which again tells us that this is an even function. Now I do want to show you a little trick with polynomials. G of x is a polynomial. You can just look at the exponents. If all of your exponents are even, then the function is an even function. So that's a little shortcut with the polynomials. All right, let's talk about odd functions. These graphs all represent odd functions. So remember, the symmetry here is that these graphs are symmetric with respect to the origin, meaning if we rotate the graph 180 degrees, it will land on itself. It will look the same. And notice that is exactly what happens when I rotate these graphs 180 degrees around the origin. We end up with the same graph. Okay, algebraically, we can tell if a function is an odd function, again, by replacing f with negative x, but this time, the equation would simplify to be the opposite of the original function. Okay, so that means that the sign of each term is going to be the opposite. Let's look at our first example. F of x equals 3x plus x cubed. So again, we're going to replace x with negative x. And then we're going to simplify. 3 times negative x is negative 3x. And if I have a negative base raised to an odd power, that's going to result in a negative value. So negative x cubed would equal negative x cubed, or I can write it as minus x cubed. Okay, so if you compare what we ended up with to the original function, I hope you're seeing that the sign of each term is now the opposite. So again, that is telling us that this is an odd function. F of x is actually a polynomial, so again, we can use that little trick by looking at the exponents. Now, the exponent on this x here is a 1. It's understood to be there, we just don't write it. And so if you look at your exponents, 1 and 3, they are both odd. So this is an odd function. Okay, next example, g of x equals 2x minus x times the absolute value of 2x. So again, replace x with negative x. And let's simplify. 2 times negative x is negative 2x. If I'm subtracting a negative x, that'll change to a plus x. On the inside of the absolute value, 2 times negative x is negative 2x. But remember, absolute value is always positive. So, I mean, the absolute value of negative 2x is going to be the same as the absolute value of 2x. And so now, if you compare back to the original equation, you can see that the sign of each term is now the opposite. And again, that tells us that this is an odd function. Okay, now the last thing I want to show you is that it is possible for a function to be neither even nor odd. I mean, graphically, that would just mean that the graph does not have the two types of symmetry. It's not symmetric with respect to the y-axis, and it's not symmetric with respect to the origin. Algebraically, that would mean if we replace x with negative x and we simplify, we're not going to end up with the original, and we're not going to end up with the opposite of the original. Okay, so here are a few examples for you. Let's say f of x equals 3x squared plus x. Again, if I replace x with negative x, and I simplify, negative x squared is positive x squared. So my first term I can just write as 3x squared. And then I'm adding a negative x, so that'll change to subtracting x. And so if I compare to the original, like I can see that the sign of this term is now the opposite, but the sign of the first term stayed the same. So we would say that this function is neither even nor odd. Okay, let's look at g of x. Again, replace x with negative x. Simplify 2 times negative x is negative 2x. If I have the absolute value of negative x, that would be the same as the absolute value of x plus negative x squared is positive x squared. And so again, if I compare to the original, I can see that the sign of the first term changed, but the sign of the second term stayed the same. So we didn't work back to the original, and the sign of all the terms did not change. Okay, so again, this function would be neither even nor odd. All right, so you guys, we will definitely practice this in class. As always, thank you for watching, and have a good night.